Alright, welcome to my channel, and we're gonna be talking about the number one. Okay, let's talk about one and trying to see if we can solve the age-old question about, is one gonna be prime? Is there a, is there or let's put it to you this way. Let's give it away. Let's just give the whole story plot away. Is there a way? Is there a conjecture to solve all prime number theorems? I mean, okay, so that's the whole point about all this. And can one be prime? Is there another question? Is right now is a conjecture that they can prove one is prime, and if proving one is prime, is it gonna solve all the prime number theorems? Yeah, cause seems like it. I mean, I don't know. Once, like, if you divide one by one, if you divide one by one, it's just gonna give you one. One divided by itself, and one. Technically, it's kind of like a dead giveaway that one's gonna be a prime number. But who knows? Like for example, like you can go into this deep search whether, like, dividing by one, do you have an object dividing one, or do you have something substantial? Because usually if you have one on one, is one imaginary. Like, for example, if you have one car divided by one, what does that mean? Is the one imaginary, and the one car is a substance? So does the divisor, or forgetting my vocabularies, but is the number dividing the divisors are gonna be imaginary? Well, who knows? Since we're not here to teach math, it's gonna be pretty. It seems like a pretty good subject to go to do pretty much try to solve that particular issue. And is there a conjecture to solve all prime number theorems? Like, can you use the same theorem to solve all prime number theorems? Is it gonna be solvable? Because most of the time, if you're talking about, let me see here, we have here we can go into this one. Are they all even? Are all even numbers the sums of primes? Okay, so see, I previously did state that number two is excluded from the sums of prime equals even numbers. So does that mean that 2 somehow gets magically excluded out of the conjecture? Because usually, like, 2 can only be written as the sum of two prime numbers, either 1 plus 1 equals to 2. And what does that make 1? If you can prove that all even numbers except for 2 are the sums of primes, even though mathematicians consider that the number 1 is not prime. So does that actually prove that 1 is prime, or is 1 going to prove all number theorems? For me, it's a pretty much a good question. It's a good topic to think about some lonely nights. Let me see here. Collex conjecture here also as well. As you see, I haven't done anything from the last video, but generally speaking, this is what we okay. So this is the pretty much what I think I put the highlights, the actual cherries on this particular prism. And if you notice, I wrote down the equation. It is kind of similar to the perfect prime, but that's kind of like or a Fibonacci kind of sequence. But if you notice right here, if you have noticed right here on here, so you're pretty much doing you're pretty much doing a lot of a lot of the x x a lot of that x squared where like, well, kind of like, no, you just went there different way, should have gone this way. Then let me see here. Okay, so you got 1 2 3. So basically, if you can do the roots pretty much is what I'm going for. Roots, square roots, cube roots. So you have, I forgot how this goes. It's gonna go, it's like 1 square. See, it's the square root or something. 2. Oh yeah. Oh yeah. It's gonna be 2, and then x, and then x is equal to 1 2 3 4 5, and then etc. Yeah, so let's see. I don't know, I think I butchered that. So see, all that particular right there, it's gonna be so so basically 2 being square by square. So if you get 2 square, it's gonna be 4. If you get 2 1 square, it's gonna be 2. And then I think 3 square would be 3 square. Is that right? 2 8 4 8. 4 is 8. 3 is not 3 times. I forgot how. I actually do forget how that is actually going. 1 2 3 8 16. It's kind of similar to that, except for the 8. 8 is cubed actually. It's actually cubed. Oh. So let me see here. 1. Where's that backwards? Oh no, that's backwards. Yeah, I think I have a bunch of. Yeah, I think that's what we call that backwards. I think I had it backwards. Yeah, and then just switch some stuff around. I don't have to write stuff. Then let's just get rid of all this crap. No. Great. So here we go. Okay, so that's pretty much that right there. 1 2 3 4 5. So your one square and two square, uh or is it, yeah, okay, yeah, that one's messed me up. Okay, that's what I see. Let's see what it is. It's gonna be two. So and you have two square before, three square be nine. No, it's actually not that. Yeah, either. For some reason I thought it was something like that, but at this point, but never mind. I think I messed up, but pretty much conjectures here. Well, usually if you're gonna go with the Collex conjecture here, is that if you run things backwards, you start getting prime numbers as connecting to some roots, or this, pretty much this equation right there. Basically you go 21, pretty much 21 is not prime, but you do get prime numbers in some of these, because if you state that the rules are, yeah, two odd numbers will give you an even number. So, and then if you keep dividing even numbers, it's going to give you to an odd number. So it's kind of provable. You can go in there. Already pretty much since pretty much the whole Collex conjecture, depending on odd number being multiplied by 3 plus 1, so you can get an even number. 3 actually, anything divisible by 3, any odd numbers, pretty much all the odd numbers are divisible by 3 except for primes, so that excludes all primes if you're dividing by 3 and taking away 1, so you can get an even number, or you can get an odd number. So if you do things backwards, I don't have, if I could edit videos, I could probably show this, but a lot better. But yeah, 1 goes to 1 there, so it's kind of showing that it's not going to end in prime, but you do get primes. But pretty much 3 does not divide prime, so for even numbers, it seems like it would go on forever, because you just get all the even numbers, and then you get all the whole numbers, all the whole natural numbers in there. So except for that right there, I kind of messed up right now. I don't think I have it all together there. So I really need to work on this so that I can get some proof on this. But yeah, because the number 3, see there, if you do this backwards, it gives you this. So if you do it backwards, so if you keep adding doubling the previous number, that's pretty much what it's doing right there. It's doubling the previous numbers. So if you take that number divided by 2 it's going to give you to 1. And if you do this one backwards, so it's supposed to give you an even number. If you do that, so you can take an even number, take away 1, and then divide it by 3, and it's gonna pop out all of these numbers. It's gonna give you the whole entire spectrum of numbers here that will connect to 1. So but since 3 cannot divide primes, it becomes apparent that these even numbers are going to give you prime numbers. See right here. So if you take away 1, take away 1 from 2 is prime, divided by 3 is not divisible by 3, so it's going to pop you up a prime. So 4, take away 1, divided by 3, okay, yeah, kind of seems like 4, it's the exception because it gives you the loop. But 8 as well, 8 take away 1 is 7, divided by 3 gives you a prime. So there's a particular special, there's gonna be like a particular special prime that would disqualify all odd numbers for making the Collatz conjecture true on all natural numbers. Not all whole numbers are natural, and they are odd. Because eventually, like, all the even numbers are gonna start showing up and popping up and ending on odd numbers, I believe, if you actually do this correctly. I haven't had time to do it. I don't really have time to do anything. Mostly try to stay away from people. See, right now I have a lot of stuff in my plate in my life, so I don't really have a lot of stuff going on for math. So, and let me see here. Oh, this one. Did we do that? Collatz. Can one be prime? Oh, see here. Let's go into. Is it a perfect number? And we come back to this right here, prime numbers. It's another prime number theorem. Is there going to be is there an odd perfect number? Is it going to be? I haven't had proof. I tried to get some numbers, and this is the closest one I had to get to 117. So could it be it's close to a perfect number to what I was saying, but then Joe was saying this right here, so it's kind of close to the particular statement that I was saying. 31 is prime, 1 is kind of prime, so the 1 actually just popping out, if you want to say that it's prime. 9, 39, see, it's at 439. 39 is not prime, so you get where I was saying this odds and primes into a perfect number. So and surprisingly there's not even numbers on this one too. Actually, you're not really getting a lot of even numbers, but we think other odd numbers are divisible by 3 and 9 and prime numbers. So also more proof that like once you start adding more more primes and the multiples of primes showing up here in the long run contributes to the prime gaps, because pretty much if you go from 1 to go list of primes and you don't put the even numbers there, prime gaps are kind of like popping more. See, it goes from, you can go from 0 gaps to, but this one's taking out all the even numbers, so they stay pretty close. And then it states all the twin primes right here. That's a twin prime, that's a twin prime, so that would be a gap. So the next, see, here we got a prime number, just 11 is divisible by 11, or that divisible by 11. So which one's next? 22. 22 is the one, and adds another gap, so it's kind of weird that you get primes here. So I mean, you could, and then See, so if 1 is prime, and here's the thing about this theorem: if 1 is prime, this conjecture here, so if 1 is prime, and then the question becomes, is 1 a perfect odd number? Because 1 is divisible by 1. Does that actually prove that 1 is prime? Because because we're getting a lot of prime numbers here that don't divide. So in my previous statements, prime numbers can never be perfect. Actually, does it disprove perfect numbers? And does it answer the question that 1 is prime or 1 is not prime? Because if for a odd perfect number and it's prime, then it's a perfect number, but then 1 has been excluded to being a prime. So see if this a conundrum here, because I don't have quite the words to describe this, but like, so if you want to prove that 1 is a perfect number, because 1 is divided by 1, so the only sum is 1, because you don't really have divisors, pretty much. Anything that will pop up once, so it's 1 plus itself divisible by 1 itself. So that's why a prime number can never be a perfect number. So does that make 1 prime if it's not a perfect number? That is one of the evidence. That is the theorem that could probably solve all prime number theorems. I'm not sure. You can have all like twin. You can also have the twin prime conjecture, and then you have all that 60 prime conjectures. So maybe, but I have no idea how would that be. Like, even the writing the proof, those for me, just being an enthusiast when it comes to math, it's still beyond my general comprehensions of how you would write a proof that would prove all prime number theorems to be solved by one conjecture or one proof. So those are the kind of the questions that I'm asking right now, if 1's gonna be prime. Because if 1 is not a perfect number, does that mean it's a prime number? Because prime numbers can never be perfect numbers. I pretty much stated there. So and that is the food for thought right now. I highlighted all the cherries, everything that I've done in a couple of months. So is there further evidence of the conjecture of this conjecture? Can 1 be prime? Is that more evidence that 1 is prime? Is it? Yeah, I hope so. And that's it. And just to recap, is there a conjecture that can solve all prime number theorems out there? If there's one prime number theorem, can 1 solve all prime number theorems? I'm not sure. I'm writing this question. I'm thinking it's not going to be true, but just even thinking of the proof is giving me a headache. So, adios.